we will see how we can apply the principle of mathematical induction to prove algorithm correctness. So first of all, let's talk about the two pieces that we have here. What is an algorithm and what is correctness? An algorithm is a program or a sequences of steps that we are going to perform, and normally we are building algorithms knowing what kind of result we would like to see. What does it mean for a sequence of steps or a computer program to be correct? So what do we mean by correctness here? And more importantly too, afterwards, how do you know that your program is correct? So let's say you wrote a bunch of code and it outputs a number. How do you know that the number is correct? How do you know that you didn't make any mistakes in the middle, or the computer didn't do something that you didn't intend it to do, and the output is the thing that it's actually supposed to do as per your desired program? Proving the correctness actually consists of two steps. First of all, we need to prove that the program will terminate. So it's not going to go on an infinite adventure. And secondly, we need to prove that it will always produce the correct result. If we're only proving number two, that's called the partial correctness of the program, which means that at every single step, we do have the correct result, but we might not actually end up stopping the program in time. So the first thing that we're going to talk about here is the loop invariant. Those of you who have taken computer science courses already probably have seen what a loop is. A loop, there are several types of them. The ones that we're going to work with most is the while loops. So a while loop is followed by a condition, and then the actual loop sort of internal works. So the condition is going to be checked as you enter the loop, and then as long as the condition is satisfied, you're actually going to go through the lines of code in the loop. So here you notice that we're beginning and ending. So this part of the program is the inside of the while loop. And as long as this condition holds, you're going to perform this line. And then you're going to check the condition again, you're going to perform these lines, and so on and so forth. We're going to go through this example with actual numbers just to see how this works in a minute. Now, with loops, we're going to let n, in this case, denote the number of iterations of that loop. So how many times have we actually gone through? Is going to be denoted by n. And as the actual algorithm gets executed, so as we go through line by line, we notice that, of course, variables change. We might subtract variables, or we might add variables. We can increase them by one, decrease them, and so on and so forth. But within the loop, the relationship between variables remains unaffected. So while we can change them throughout, there is something that they have as a relationship that binds them together that remains unaffected. And that is what we call a loop invariant. So while the numbers might be different, the fact that we, for example, will be adding them will always stay the same. And that is something that we denote by P of n. So n is the number of iterations of the loop. P of n is the loop invariant through the n iterations of the loop. So let's take a look at the example. It's going to become a lot easier to think about once we have a specific algorithm we're considering. This algorithm performs a multiplication of two numbers. So we give it numbers x and y, and the claim is that as we go through, the final output of the algorithm will be the product of the two numbers x and y. First of all, before we actually read the algorithm, let's think about how we might compute a product of two numbers. So if I give you two numbers, let's say x is equal to 2 and y is equal to 3. How do we actually compute the product? Now, these numbers are very small, so you're just going to say, well, 2 times 3 is equal to 6. But how do we know what that actually represents? Let's say that the only operation we had available to us was an addition as the basic operation. How can we turn a product into addition? If you think about this, you'll remember from years when you first learned multiplication that multiplication is actually just repeated addition. So 2 times 3 is nothing but 3 added to itself 2 times, or it's 2 added to itself 3 times, right? So you get to pick what represents the number and what represents the number of times it gets added to itself. But either way, either 2 times 3 or 3 times 2 will give you the same product as a result. And this is going to be the base operation used within this algorithm. So keeping this in mind, let's actually see how the algorithm is going to work. So I'm going to initialize it with x equals 2 and y equals 3. And then let's go through the algorithm line by line. So first, the variable called answer is going to be assigned a value of 0. The arrow represents assignment. So we're going to initialize that. And then the next line tells us that we're going to initialize I, some variable I, to be equal to 0. And then we're actually entering this while loop that we will stay in as long as the condition holds. So let's see, does the condition hold at the beginning? So it says while I is less than x, we're going to do something. Is that true in our case so far? So the first time I enter this loop, I have that I is equal to 0 and x is equal to 2. I'm going to plug both of those numbers into my while condition. So as I enter here, I have I, which is 0. Is it true that 0 is less than 2? Yes, it's true, which means that I will actually go through the while loop and compute the next lines of the code. So the next line says answer is equal to previous answer plus y. Let's write that down. So I have that answer is equal to what answer used to be, which in our case is 0 so far, plus y. And y in our case is equal to 3. Okay, I've computed this line. I mean, obviously, I can actually do the math in my head here, equals to 3. And then the next line of the code says I is going to be incremented by 1. So the new I is equal to the old I plus 1. So I is equal to I so far, which is 0, plus 1. So altogether, it's equal to 1. And that is the first iteration of the while loop. Now what's going to happen next, of course, is I've exited the loop and I'm going to check whether the condition holds again. If it still holds, I will perform the operations in the loop again. And if it doesn't, then I will end the algorithm and output the answer as the actual final output. Okay, so let's check the while condition again. Now remember that I've actually updated my values here, so these are now the values I'm going to check against. So is this true that I still have I is less than or equal to x? So my I now is 1, so I have 1 is less than x, which is still 2. I haven't actually changed the value of x anywhere here. So 1 is less than 2. Yes, indeed it is, which means that I will enter the loop again, and I will have to perform the same calculations again. So my answer is going to be my previous answer, which was 3, plus y, which is 3. So I'll have 3 plus 3, and I will again increment the I. So I is going to be now the previous I, so 1 plus 1. Okay, and of course, again, I can compute these numbers. Let me shift everything just a little bit so I can squeeze in the numbers. So what am I going to have here? I'm going to have 6 and I'm going to have 2. Okay, next up, once again, we finished the while. We're going to enter the while loop again and check whether the condition holds. So now my I is 2 and my x is still 2. So is it true for the condition here that 2 is less than 2? No, 2 is not strictly less than 2. 2 is equal to 2, which means that this condition no longer holds, which means that I will exit my while loop without not performing any of the operations here. I will simply skip all the operations. I can't enter the loop. I simply will have to exit straight out of it. And that means that the last value for the answer is my final output. So what I will output here at this point is the fact that answer is in fact equal to 6. So notice that this is, again, as I mentioned earlier, the repeated addition way to do multiplication, right? I was adding 3 to itself this many times. What I was checking in the loop is whether or not I've already added 3 to itself enough times. So my I represented how many times I've added 3 to itself so far in my loop. First, I haven't added it at all, so I had 1 copy of 3. And then once I've added it once, I've added a second copy of 3, and then I was done. because I've already added two of them together, which corresponded to x here, which means that I've added them exactly enough times, and that will be my final answer here. Okay, well, this is all great, but once again, how do I know that this is actually correct? All I've done so far is check it on two numbers, and fairly small ones at that. So how do I know whether or not my loop will always work the way that I think and believe that it should work? Let's assign some variable names to the parts of this algorithm. So instead of just the answer, what I actually want to think about is what is the answer n iterations of the loop. So the answer here on the first iteration of the loop was 0. The answer here on the second iteration of the loop was 3. And the answer here in the third iteration of the loop was 6. So as I mentioned before, between 0, 3, and 6, obviously these numbers are different, but notice how the way that we obtain these numbers always stays the same. So what I'm going to do is I'm going to let a sub n represent the value of the answer after n iterations. I'm interested in what it is after a certain number of times I go through the loop. And I'm also going to relabel I to not just be I, because I don't want it to know just what it is at the end. I want to know what it is while my program is executing. So it's going to be the value of I after n iterations of the loop. Let's say of the loop. So again, for example, in our case here, A1 is going to be what? Think about that. I1 is going to be what? If I'm interested in what the actual value of answer was after one iteration of the loop, it means that I've performed this iteration of the loop, and my answer, the value for the answer is going to be 3, right? I've completed this iteration of the loop. I've updated my answer to be the first thing through. After the second iteration of the loop, it's going to be 6. I, after the first iteration of the loop, is 1, and after the second iteration of the loop is 2. Excellent. Now, I'm actually going to make a claim. I'm going to claim that an, the answer, is the number of iterations of the loop times y. So this y, again, remember, is the number that I'm multiplying. So what I'm saying here is that after n iterations of the loop, I have multiplied y, or I've added y to itself, I sub n times. So here I've added it to itself once, here I've added it to itself twice. If x was, for example, 20, then my claim here is that after, let's say, 17 iterations of the loop, I would have added y to itself 17 times, okay? And then if that is in fact a loop invariant, then I am in good hands, because that means that after 20 iterations of the loop, I would have added y to itself 20 times, and that of course is exactly the multiplication that I'm looking at. So my claim is that this is a loop invariant. So again, invariant doesn't mean that it's constant, it just means that this relationship holds for every single iteration of the loop. Whether I am in iteration, let's say 9 or 17 or right at the end 20, it's always gonna have this relationship embedded in it. Okay, so this is what we will refer to as P of n. And you're hopefully already beginning to guess at the fact that if I am to prove some property for any natural value n, then this is a good application of the induction. And that's exactly what we're going to do. So remember that for the induction, I have to have a basis step, and then I have to have an inductive hypothesis. I'm going to write them all out specifically here because I want to be able to refer to them later. Then I'm going to write down what it is that I need to show. And then finally, I'm actually going to perform the inductive step. All right, basis step. So I am looking at proving that Pn the property Pn holds for all n greater or equal than 0. Notice how my initialization values here are 0, so that will be my first value to check in the basis step. So I'm going to check it when n equals to 0. So what happens when n equals 0? This is before I've ever gotten to the while loop. My answer and I value are 0. So I have that a sub 0 is 0, and I have that I sub 0 is also 0. And the thing that I need to check is whether this relationship holds. So is it true that a0 is equal to I0 times y? Is that actually true? Well, a0 is 0, I0 is also 0, and y is whatever y is. But 0 times anything is 0, so this is in fact true. So I can replace my question mark with a check mark, and the basis step actually holds. Once we've shown the basis step, we can move on to the inductive hypothesis. Remember that in the inductive hypothesis, all I'm doing is I'm going to assume that P of k is true for some k that is at least as big as my base case, which is 0. What that means, let's write out what pk being true means, is this property holds for the kth loop iteration. So it means that a sub k is equal to I sub k times y. What we need to show is that p of k plus 1 is also true. And what that means, I need to show that a sub k plus 1 is equal to I sub k plus 1 times y. Excellent. I have a little equation that I need to prove is correct. So I'm going to start with the left-hand side and see if I can get down to the right-hand side here. So starting with the left-hand side, what do I have? I have a of k plus 1. How do I go about obtaining a sub k plus 1? Well, let's go back through the loop. Remember that a corresponds to the answer after n iterations. So a sub k plus 1 corresponds to the answer after k plus 1 iterations. So I have k plus first iteration of the loop. Going back, the way that I obtain the answer to the next iteration is by adding y to the previous one. So if I am in the k plus first loop, it means that when I entered here, I had to perform this operation on the answer. So in the kth iteration of the loop, I had a sub k plus y coming straight from this line 5 of the code. And that is actually something that I'm going to write down. This is line 5 of the code, so I can clearly refer to it. Now, it looks like I'm going to also have to involve I sub k plus 1 into this arithmetic. So let's see, what does I sub k plus 1 equal to? Same logic, I will have entered this loop on the kth iteration and increased I by 1. So I sub k plus 1 is actually I sub k plus 1. And this comes from line 6 of the code. Now, with this information, I can now go back to the equation that I actually want to use. I want to connect these two variables by hopefully somehow referring back to the inductive hypothesis and using that to my advantage. So let's go back here, and I'm going to start with what is a sub k plus 1. Now, let me just move this a little bit out of the way here. Perfect. So what I'm going to have, a sub k plus 1 is, according to this, a sub k plus y. Now, once I'm down to here, this is really great news because I can use inductive hypothesis here directly. I can simply substitute a sub k with the expression that I've assumed is true for it in the inductive hypothesis. So here I have I sub k times y plus y, right? So this is a sub k, and this step can be performed by inductive hypothesis. Excellent. Now I notice that both of these terms have y in them, and that is something that I can certainly factor out. So I'm going to have, if I factor that out, I'm going to have left I sub k plus 1 times y. right? I factor it out onto the right-hand side here. And now this is also quite helpful because I know from what I've derived from the algorithm that I sub k plus 1 is actually just I sub k plus 1 in the subscript times y. And this, of course, is fantastic news because now I have that a sub k plus 1 is equal to I sub k plus 1 times y, which is exactly what I needed to show. So that means that by the principle of mathematical induction, I have proven that Pn is a loop invariant for all n greater or equal than 0. Now, that is fantastic news because in particular, that means that P of n is true when we exit the loop. So let's write that down. Therefore, P sub n is true when we exit the loop. And what that means, of course, is on the last step, the answer will be computed as per the loop invariant. So when do I actually exit the loop? Let's see here. Remember that I went up to 1 is less than 2, and in my next step, I had 2 is less than 2, which was wrong, and that's when I had exited the loop. So we will exit the loop. The loop will terminate when I have equality here. And that is exactly when I is equal to x. Okay? If this is my loop invariant and I exit it when I is equal to x, that means I exit it when I can be replaced by x, and therefore my answer will be indeed x times y, which is exactly what I was looking for. So what I have is answer is equal to, again, as per the loop invariant, I times y. And on loop exit, I have I is equal to x, so I have x times y. And that, of course, is exactly what I wanted to prove. And we're done here. One other thing to notice is I have not specifically talked about the fact that this algorithm will terminate. But that is fairly clear based on a structure. I am starting with I equals 0 and some finite number x. In every iteration of the while loop, I am incrementing I by 1. So eventually, I will reach the case of I equals x, at which point I will in fact exit the loop. So this is not going to go on forever because I'm bounded by the less than here. And I am increasing the I up until my ceiling here of the value of x. So the loop will certainly terminate, and as per the proof by mathematical induction, it will in fact terminate with the correct answer. So what we have just seen is what we'd normally call an iteration method, where we use some kind of initial value. So in the previous problem, it was answer being set to 0 and I being set to 0. And then we use it to generate a sequence of successive values. So in our last case, it was 3, and then 3 plus 3, so 6. And if I was multiplying 3 by a larger number, I would keep adding 3 to itself until I've added enough times to produce a multiplication. The other place we've actually seen this already is computing n factorial. We have noticed that n factorial has this kind of successive structure that if I just multiply the numbers by themselves, then to produce the next factorial, all I have to do is use the previous one multiplied by the number that is 1 bigger, and I will have the next factorial available to me. So this algorithm is for, in fact, specifically computing the factorial. We are going to set a couple of variables right away in the actual statement of the example. We will let fact of n be the value of the factorial at the end of n iterations of the loop. So kind of like a sub n was our answer last time. Fact of n will be our factorial so far, n iterations into the loop. We're going to prove that Pn, which is defined by the fact that what we have at the end of the n iterations of the loop is in fact n factorial. We're going to prove that that's a loop invariant. So it means that if I've performed 4 iterations of the loop, then at the end of it, I have 4 factorial, and so on and so forth. Now here is the algorithm as is given to us. Let's see if we can make our way through with a particular number. So let's say we actually want to compute factorial of 4. So my value for n is going to be 4. Let's see what I have here. We're going to start off by setting factorial to be equal to 1. So let's in fact write down that value. And the next up, we have that I'm setting I to be equal to 1. After this, I'm going to enter the while loop. So once again, I have the condition. I'm going to check whether this condition holds. If it holds, I'll perform the operations of the loop. If it doesn't hold, I will simply exit the loop immediately and output whatever factorial value I have at that point. So my while loop will check whether or not I is less than n. So what do I have so far? Let's see. Currently, my value for I is 1 and my value for n is 4. So in the first check for the while loop, I'm going to check, is 1 less than 4? Yes, indeed it is, which means that I will actually enter the loop and perform what the loop tells me to do. So first thing first, I'm going to assign I to be I plus 1. So that means that my I will be what it used to be, which is 1 plus 1. So I will become 2. And the next line says that my new value for factorial will be what I had as a factorial, which is 1 times I. Okay, so my new value of factorial is the old value, which is 1 times I. Now notice that I have to read all the values I have so far, and I has been updated to be equal to 2. So right now I have that the factorial is 1 times 2. And that's the end of the while loop. So I'm going to go to the beginning and I'm going to check the condition again. What I have next is, again, I versus n. So my I now is 2 and my n is still, 4. So is 2 less than 4? Well, yes, it is, which means I will enter the while loop. I will increase the value of I by 1, and then I'm going to have that my factorial is what my previous factorial was. So let me just actually keep it as 1 times 2 times I. And my current I value is 3. So times 3. Great. I've completed the operations within the loop. I'm going to re-enter the loop and check for the conditions again. Let me maybe move this around because I'm very quickly running out of space here. There we go. So next iteration of the loop, I am going to once again check my I, which now is 3. Is it less than 4? Indeed it is, which means I'm going to repeat the operations again. So increase the value of I by 1, and now my factorial is going to be what it used to be. So 1 times 2 times 3 times I, and currently I is 4. So times 4. Okay, completed the loop. I'm going to enter it again. My next step, I is equal to 4 and n is equal to 4. So in my next step, I'd be checking, is 4 less than 4? No, it's not. 4 is equal to 4, which means that I will not enter the while loop, and I will actually exit the while loop and end the algorithm, which means that my value for the factorial is the last one computed. So this is for n equals 4, and what I have is 1 times 2 times 3 times 4. Excellent. Our small example shows that at least I have some hope to believe that this algorithm is doing what it's supposed to be doing. Also notice, I pointed this out before, I am specifically in these types of examples not doing the simple arithmetic and keeping the answer not simplified, and that is because I would really like to see the structure of how the answer is formed, and keeping it this way allows me to see how I've built up my factorial one number at a time. Okay, so we've done an example, we sort of understand how the algorithm works. Again, we have some faith in the fact that it's probably correct, but we will still need to prove that it's in fact correct. We are given the very particular definitions here. Fact n is the value of the factorial at the end of n iterations. I'm also going to prove what I've been asked to prove. I'm going to show that p of n, as defined here, is in fact a loop invariant. Very well, if we're going to proceed by induction, we are going to start with a basis step. the basis step here, we don't have any value of n that we are told that we cannot enter, and the smallest factorial we've ever computed was 0, so I'm going to start with n equals 0. If I enter with n equals 0, I set factorial to be 1, and I set I to be 1. And then the next step, I'm going to check whether or not I'm entering the while loop. So my I, which is 1, is it less than n, which is 0? No, it's not. 1 is not less than 0, which means I will not enter the loop, and I will be done the algorithm immediately. So I will output the value of the factorial that I have so far, which is 1. So this will output factorial of 0, which is the value of the factorial after 0 iterations of the loop. Remember that I have never actually entered the loop, is in fact equal to 1. And that is precisely how we defined 0 factorial to be. So this is in fact equal to 0 factorial, and we're in good shape. Next up, we're going to have the inductive hypothesis. Again, I like writing it out explicitly so that I have it in front of me and I know what it is that I can use. So here we're going to assume that after k iterations of the loop, I have this relationship. So I'm going to assume that factorial of k is in fact equal to factorial of k after k iterations of the loop. I need to show that the same, but for k plus 1 in both places, holds. So I'm not going to write down what I'm going to need to show. I'm going to move on to the inductive step immediately, because this is not a very big thing to remember. It's just the same exact structure. So what I'm going to do is I'm going to start on the left-hand side. I'm going to think about what do I have as the computed factorial after k plus 1 steps of the actual algorithm. So as I'm entering the loop, notice that factorial gets computed in this line, right? Everything else is just iterating over I and checking whether or not I've entered the loop. So if I'm looking at this line, in k plus first iteration of the loop, I will have computed it as the previous factorial, which would have been the factorial after the k iterations times the current iteration, times I. Notice that for every iteration of the loop, my I is 1 bigger. I am incrementing the I before I plug it in here. So in the first iteration of the loop, my I was equal to 2. In the second iteration of the loop, my I is equal to 3, which means that in the kth iteration of the loop, my I is going to be equal to k plus 1, and that's what I'm going to plug in here. So my factorial here is going to be the factorial computed at k, but my I here will have been computed in the previous line and will correspond to k plus 1. So this is fact of k times k plus 1. Now, so this I'm going to actually annotate. This came from line 6 of the code, and this came from line 5 of the code. Now I am going to use my inductive hypothesis because I have reduced the problem to the previous step, to k, and I have assumed something about that being true. So I can replace my fact of k here by k factorial. So overall then I have k factorial times k plus 1, right? Because I've left my k plus 1 here from the previous expression. Now, remembering how factorials work, I know that multiplying k factorial, so k factorial is 1, 2, all the way up to k, and now I'm multiplying by k plus 1, which overall gives me k plus 1 factorial. So using the properties of factorial, I'm only down to the actual factorials here. I can write down that that's the case. And again, let's not forget, like I almost just did, that we have to annotate where we've used the inductive hypothesis, which was right here. Now, this is great news because I have proven exactly what I wanted to prove. I have proved that after k plus 1 iterations of the loop, I actually have k plus 1 factorial as the output, which means that by the principle of mathematical induction, what I have here is that p of n is true for all values of n above 0. So let's write this down for all n greater or equal than 0, because again, remember, that was our base case. Now that means that during loop and on exit, what I have is the computations of the n factorial. So after n iterations of the loop, I will in fact have n factorial as the final output. So after n loop iterations, we have n factorial. Okay, pretty straightforward, but you do have to go sort of through the mechanisms and make sure that you justify every step as either coming from the algorithm or coming from induction here. Next up, let's take a look at a linear search algorithm. So for the search algorithms, we're going to also introduce a notation for the list. A list has square brackets, which indicate that the elements are not like the ones in the set. They come in a bag. It actually matters what order they're in. So the list PQR is not the same as the list RPQ, despite the fact that the elements are the same, they're placed into different positions. Lists are positional. So the first element is x1, the second element in the second position is x2, and so on. Now we're saying it's unordered, not to signify that the elements have no order, but rather that the elements themselves don't go from smallest to largest or anything like that. If it confuses you for now, think about it as being ordered as a set, but again, like the elements are, while the order is fixed, the order is not of any particular sorted value. What we're going to do is we will like to search through this list and look for a particular element. We're going to call that element key. So I'm going to look through the list and look for a key. If the key, so if the element exists in the list, what I would like to do is return the location. So I would like to say something like the element 7 is in location 33. If the key does not exist in the list, I'm going to return 0. What we're going to do within this algorithm is we're actually going to search the list from right to left and check every single element along the way, whether or not it's the one we want. If it's not the one we want, we move one position to the left. If it's the one we want, then we return the location. So here is the linear search algorithm as written. And let's take a look at what these variables are. X itself is going to be our list. N is going to be the length of the list. Key is going to be the actual element that we're looking for. And location is going to be our starting value for the location here, which is going to be equal to the length of the list. So as I said, we're going to start from the right. So the location, our first default assumption for location to check, is going to be the last one. And then we're going to move from right to the left and change up location as we go. If the location ends up being 0, it means that the key wasn't there. But until we see that that's the case, we're going to initialize our location as the last element of the set. And now let's take a look at how all of this is going to work with a particular example. This is my list X, and my key is going to be element R. So I will be searching through this list for element R. It's important to realize that as a human, we perceive this list as a whole. A computer will be reading it off one element at a time. And so that is exactly what the algorithm is going to be doing. So let's work our way through the actual lines of code. This is my input, the list and the key. The length of the list in our case is 5. There's 5 elements in the list. So my n is going to be equal here to 5 for our example. Okay, and now let's see what the algorithm says. First of all, we assign x naught the value of r. Let me just make some space for myself. X naught, will have the value of r because that's our key right away. And my I is going to be assigned the value of n, which in our case, the length of the list is equal to 5. And now I have, once again, a while loop. But notice that I don't have here less than or equal to, I have not equal to. So all I'm going to be doing is checking whether the current element I am at in the list, going from left to right, is it equal to the key or not? So I start off at the end, and the idea is I'm going to look at this element. Is it equal to the one I want? No, it's not. Then I'm going to move one step to the left. Is this element equal to the one I want? No, it's not. And then I'm going to move one more step to the left. Is this element equal to the one that I want? Yes, it is. And I should be able to return the location of it, which means that I should have been keeping track of the location that I'm pointing at in the first place. And that's exactly what I is going to do. So what is it checking in our case? I is equal to 5, so I'll be looking at x5. So in the first step, I'm checking, is x5 not equal to r? x5, the fifth element in the list, is t. Is t equal to r? No, it's not. T is not equal to r, which means that I will actually enter the while loop because the condition of non-inequality holds. And what I have here is, as opposed to the previous algorithms, I'm subtracting 1 from I. So I started at 5. That means that at this step, I am going to reduce I to 2, and I'm going to update my location to be equal to I. So location is equal to I, which in this case is 4. I've exited the while loop. I'm going to re-enter it again and check the condition again. So next up, I am still checking, is xi equal to r? But now my I is equal to 4. So now I'm checking, is it true that x4 is not equal to r? x4, 1, 2, 3, 4 is the fourth element. Is this element equal to r? No, it's not, which means that I will enter the loop and go through the operations again. I'm going to reduce I by 1, and I'm going to update the location to be equal to I, which is 3. I've exited the while loop. I'm going to check the condition again to see if I should go through this again. So now I'm checking, is x3 not equal to r? x3, 1, 2, 3. x3 is right here. Is it not equal to r? It is equal to r, which means that I'm not going to enter the while loop, and I'm going to return the location that I have up until this point, which is location from the previous step. So here, I'm going to return this location, and it's equal to 3, which is, of course, exactly where the r element is. Notice that if my key was something that didn't exist in the list, so let's say 7, I would have checked every single step and I would have subtracted 1 from my location every single time. I started off with y equals 5, going through 5 steps of the algorithm. I would have subtracted 1 from it every single time. And by the end I hit the end of the list, the left end of the list here, my location would have been equal to 0. So if the key does not exist in the list, the algorithm would in fact return 0. Now, once again, this is just an example, and I would like to prove in generality that this algorithm will always work this way, and there wasn't just some fluke that I happened upon an example where it performed the way that I expected it to perform. But notice here the difference between this algorithm and the previous ones. Here, I don't really have a loop invariant. I am just thinking about how many times will I actually enter this loop. The location changes, and so I'm not interested in tracing what happens within the loop. I am interested in tracing where in the list I am. So if I start in the spot 5, and as I go through the list, that's the thing that I'm keeping track of. So for my statement, P of n, I am going to make an assumption that the algorithm, like in order for me to set up induction, that this will be actually inducting on n, the length of the list. So algorithm works properly, or correctly, let's say, for list of length n. Now, of course, your length of the list can be anything greater or equal than 0. Your list could be just empty. So when we are thinking of our basis case here, I'm going to check what happens when the list is in fact of length 0. So what's going to happen? I'm going to start with 0 here. I'm going to get through these 2 steps. My x naught is equal to key, whatever my key happens to be. My I is equal to n, which is 0. And so when I enter into the condition for the while loop, what am I checking? I'm checking if xi, so x0, is not equal to key. But I've just set it to be equal to key, which means that they are in fact going to be equal, and the while loop will never be entered. It will be completely skipped. X naught will maintain equality to the key, and that location, or 0, will be returned. Remember that if we return 0 means key isn't there, and of course for the empty list, no matter what the key is, it's not actually there. So for n equals 0, while loop is skipped, and we return the location as equal to 0. For the inductive hypothesis, this one is easy enough to say. Algorithm, in fact, let me just copy it over. For the inductive hypothesis, I will have that algorithm is working correctly for a list of length k, for some k above the base case of 0. And then, of course, what I need to prove, and I'm not going to write this down, but what I need to prove is that algorithm works correctly for the list of length k plus 1. So let's take a look at what happens in our inductive step. This one's going to be a little bit different from the ones before. So I am looking at the list of length k plus 1 now, right? So I have a bunch of elements, and the number of them is k plus 1. So elements here, let's say this is going to be my k plus first element. So because I'm working with my list from right to left, there are two things that might happen. I might find the key immediately because it's the last element, or I might not, so the key is not in the last spot, and then I'm going to be reduced to actually sorting through the list of size 1 less. Now, of course, the list of size 1 less is exactly size k, and that is where my inductive hypothesis will come into play. So the two cases are if the key is the last element or if it's not. So let's write those two down that way. So my first case is the key plus first element, the k plus first element is actually equal to key. And my second case is that it isn't. So what happens if my last element of the list is equal to my key? So the thing that I'm looking for. So as we're going through here, I'm going to be looking at the while loop. And this is actually precisely what happened here. It's always going to happen sort of on the last step, right, when we find the location. So what happened here is the moment there is equality in the while loop will not be entered. So if x sub k plus 1 is equal to the key, that means that when I'm checking here, I won't actually be executing the while loop, which means that it will return the location as stated, which will be the last location of the list, so k plus 1. Okay, so while loop is not entered, and location is returned as n plus 1, or k plus 1. Location, returned location is k plus 1, which is of course correct. All right. Now, what we have is the other possibility. If I actually do enter the while loop, so the k plus first element was not equal to the key, I sort of disregard it and I move left in my space, in my list here. Now, as I said, if I disregard the last element, then the length of the resulting sublist is now k, which means that I can apply inductive hypothesis on it, which states that this algorithm works correctly on a list of length k, which is now what I have. So in this list of length k, it will find the key and output a proper location. So that means that while loop is entered, and we are now searching through the list with k elements. And we search through list of k elements, which by induction hypothesis will produce the correct location. And we're actually done. By the principle of mathematical induction, P of n is true for all n greater or equal than 0. Okay, so just a quick recap. In this case, we actually had to use induction on the length of the list and not the particular iteration of the loop. And we had to split it into cases whether or not we will have considered the full list or the list of size k, in which case the inductive hypothesis help us simply skip straight to the answer. Next up, we're going to consider a sorting algorithm, bubble sort. So I'm going to start with a list, x1 through xn, and it's an unordered list in a sense that these elements do not appear to be increasing or decreasing. They're all kind of jumbled up in there. Bubble sort will basically take the largest element of the list and bubble it all the way up to the top, and then repeat that for all of the other large elements. So think about it like fizzy water or champagne. The biggest elements will float up to the top one at a time. Now, this is much easier to be understood with an example. So here is a set that we're going to sort using bubble sort. I have 34, 13, 21, 3, and 89. Now, this set is small enough that, of course, I know I can expect it by just staring at it, and I can sort it because as a human, I'm very good at finding the smallest number, the second smallest, the third smallest, fourth, and last. So I know that this is my eventual goal in sorting. But bubble sort will proceed by comparing elements two at a time. And if the larger one is on the left, it's going to swap the two elements. And it's going to proceed to do that for every two elements in a row until it reaches the end of the list. After that, we're going to do the exact same thing all over again. So we're going to go through several passes of the exact same two-element comparisons and swappings if necessary. So let's go through that. So the first thing we're going to do is we're going to compare x1, x2, and we're going to swap if needed. Now, I can, above these elements, write down, actually it's better if I write down x1, x2, x3, x4, x5, just so that we know that each one of these corresponds to a particular position. So I'm going to compare 34 and 13, and I'm going to arrange them in increasing order if necessary. So 34 is bigger than 13, which means that I will swap them, but I'm not going to touch any of the other elements. So I'm really working with the set, or with the list, two elements at a time. And then I'm going to go to the next pair. So I've compared x1 and x2. My next pair is x2 and x3. And I'm going to do the exact same thing. I'm going to compare x2 and x3, and I'm going to swap if needed. So what is going to happen here? Now, my list has been modified, so I'm looking at my current list, not my original one. So I'm comparing x2 and x3. Do they need to be swapped? Yes, 34 is bigger than 21, so they indeed need to be swapped. So I'm going to have 13, 21, 34, 3, 89. Again, I am only concerned about the two current elements that I am comparing, while the rest of the list will stay as is. Okay? Excellent. Next up, I'm going to compare x3 and x4 and swap if needed. So I'm comparing, where's my highlighter? There we go, x3 and x4. Am I going to swap them? Yes, because 34 is bigger than 3, so I'm going to swap them. So I'm going to have 13, 21. Here's where the swap occurs, and 89 stays in its place. Next, I'm going to compare x4 and x5 and swap if needed. So these are the two elements I am comparing, but they're already in the right order. 34 is less than 89, and so I am not going to do anything. In this case, swapping is not necessary, so my list is going to stay as is. And this is the the first pass of the algorithm. So notice that what this has done, because I've checked all the way up until the end, is I can now be sure that the largest element is in the last position. It's in its proper position, because I've compared everything else to it, and in this case, 34 bubbled all the way up to here, but couldn't surpass 89. So that means that here, largest element is in the right spot, is in correct position, whereas the rest of the list still remains to be sorted. And this also gives you some idea of how later on we will prove it by induction. I have already placed my largest element, and now all I have to do is sort the list of size 1 less. So this would be a natural application for the inductive hypothesis of the induction proof. But not until later. Let's go through the second pass of this algorithm. I'm not going to write out all the steps. I'm going to say second pass. We'll also compare everything, ... And what I claim I will have after second pass. And I encourage you to actually go through all of the steps and ensure that this is what it looks like. I'm going to have 13, 3, 21, 34, 89. So after this pass, I know that the last two elements are already sorted. So they're in their proper positions, because at every single time, I will take one element from existing ones and I'm going to place it in the right spot. After my third pass, again, it's going to take some number of steps. My list is going to be 3, 13, 21, 34, 89. And because I've bubbled up 3 elements, I know that the 3 tops ones are already sorted. Okay? Next up, I'm going to have another pass and another pass. And so at the next pass, I'm going to move over here. I'm going to have 3, 13. I mean, I know I can, by inspection, see that it's already fully sorted, but my algorithm doesn't know that yet. Notice that it knows that this is now sorted, so the 4 elements here are sorted. And at the last step, everything will now be sorted, right? So the next step will be all sorted. So a couple of really important observations here that will be useful for the proof is after no matter how many passes, so for example, after 3 passes, 3 top elements are sorted and placed in their proper positions. So overall, it's actually going to take me the length of the list minus 1 pass, because sorting 1 element is not like sorting anything at all, right? So this is what's going to be my important thing to remember in the actual inductive proof of the algorithm. Again, this is just the actual statement of the algorithm. You notice that this is my 2x2 comparison, and I have my swap here. And now we're going to proceed by induction to show that this actually will produce a sorted list in the end. What my statement on n is going to be is that this algorithm correctly sorts lists of length n. List of length n. So as in the previous example, we're going to use the induction on the length of the list in total. So what is my basis step here? So notice that in my sorting algorithm, I take 2 arguments, the list itself and the length of the list. So what can my length be here? If the length of the list is 0, then as I go through the algorithm, I notice that in this for loop, I'll have going from 1 to -1, which of course isn't possible. So the smallest possible thing I can have is the length of the list equals to 1. If the length of the list is equal to 1, so I have only 1 element, there's really nothing to sort. So at this point, I'm really hoping that my algorithm essentially does nothing, because a list of 1 element is always sorted. So what do? If n is 1, then I will go from 1 to 1 minus 1, 0. So it's not going to do anything. It's not even going to enter the for loop, but at least it's not creating negative numbers. Not going to enter anything, not going to actually do anything. So it will produce the properly sorted list, which is the one that it started with in the first place by default. In my inductive hypothesis, I am going to assume that pk is true. So that means that I'm going to assume that the algorithm works correctly for lists of size k, right? Of length k. Let's write it out. Algorithm works properly works correctly for lists of length k, and here it has to be above my base case, so 1. And then, of course, what I would like to prove is that the algorithm works correctly for lists of length k plus 1. So I'm not going to write this down. I'm just going to jump directly into inductive step. It's easy enough to remember what it is that I need to prove. So I need to prove that it works on lists of size k plus 1. So let's make such a list. x1, x2, and so on and so forth, xk, xk plus 1. So I need to show that my algorithm will work properly on this list. Now, let's take a look. So I have k plus 1 here. So k plus 1, what is the smallest number that this can actually be? Notice that I'm assuming that k is at least 1. So k plus 1 is going to be at least 2. Now, this actually means that there's something to be sorted. My list is going to be of length at least 2, so it has at least 2 elements there. So by default, it's not sorted. I actually will have to go through the bubble sort. Now, because this algorithm is so complicated, there's 2 nested for loops and an if loop, we're going to go a little bit more hand-wavy here and look at our intuition from the example. So this is not going to be quite the rigorous proof, let's say, but I just want you to see how to actually use induction here. So remember that after the first pass of the algorithm, which now will certainly happen because the list is at least 2 elements long, after the first pass, I've placed the largest element in this proper spot, in the last spot. So that's the first thing we're going to notice, is that because my list has things to be sorted, my algorithm will execute, and what we will have, even if you trace it through the for loops, which again I'm not going to do, the largest element will be placed in the proper spot. Largest element, and in fact, we know exactly which spot it is, will be placed last in the spot that is labeled as x sub k plus 1. So this is where the largest element will go. So what does my list look like now? Remember, in the bubble sort, at every single step, I actually change up my list, so the order changes. If it placed the largest element in the last spot, what I'm going to have now is x1, x2, blah, 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 xk, and then whatever element was the largest. And this, of course, is fantastic news because the largest element has been placed, which now means that I have k element list to sort. And of course, by induction hypothesis, that is exactly what we've assumed the algorithm already can do. So by induction hypothesis, algorithm bubble sort will properly sort this sublist of k elements. Now, if the sublist of k elements is properly sorted in the increasing order, and this element is the largest, of course, what I have altogether is that this entire list is properly sorted, and therefore the algorithm works correctly. So by the principle of mathematical induction, the algorithm works correctly for all lists of size at least that of the base case, so in this case, 1.